Please note that filming text on a whiteboard requires extremely bright studio lighting. Subsequently, sunglasses were worn during the filming of this video to prevent damage to my retinas. A note on how to use these sessions. Jot down the notes as we go, so we'll help you learn the material in a more interactive way and you can use them as study notes later. Also, in the small chance that a discrepancy arises between the professor's notes and mine, always go with your professor. They're the one grading you. Lastly, any examples or analogies used in this session are not meant to support or criticize politics, religion, or lifestyle. They're merely learning tools to help understand the material. Alright, guys and girls. It's time to get cracking.
Okay, so that finished up part 1 of OChem Basics, reactivity. Today's session we're going to be talking about OChem Basics part 2, covalent bonding, okay? How bonds form and why. And we all know that compounds are formed by bonding atoms together. So the first topic I want to cover is the shapes and angles that these atoms bond together in. Because atoms don't just bond together any old way. They have very specific shapes and orientations when they join together. So hey, whenever you're asked about the shape of a compound or its bond angles, I want you to think about something called VSEPR theory, okay? So hey, does anyone remember what VSEPR theory is? Or what it even stands for? VSEPR theory. Okay, so let me just break it down for you guys. VSEPR theory, this stands for valence shell electron pair repulsion theory. And whoa, when you say it like that, no one's going to understand what you're talking about, okay? So, hey, when something sounds complicated, I always try to break it down into the simplest possible pieces, okay? So, hey, if we take this a couple words at a time, you guys, VSEPR theory, this stands for, okay, so we have VSE, and that stands for valence shell electron. Okay, and valence shell electron, this is just another way of saying the outermost electron, right? The electron is used to bond with other atoms in a reaction. Okay, so that's valence shell electron. Then we have P, which stands for pair, right? So a valence shell electron pair, because electrons come in pairs, right? And hey, finally we have R, which stands for repulsion. Repulsion, okay? And hey, you guys, electrons are negatively charged, right? And negatives repel other negatives, right? So, hey, all VSEPR theory is saying is that the outermost electrons, which come in pairs, form bonds that repel each other, okay? More simply put, electrons in bonds repel electrons in other bonds as far apart from each other as possible, okay? So, hey, let's write down this layman's definition, because this is saying that electrons in bonds repel electrons in other bonds. And duh, this is kind of common sense, you guys. Okay? Alright, so one more time, you guys, valence shell electron pair repulsion theory. All this is saying is that electrons in bonds will repel electrons in other bonds as far apart from each other as possible, okay? But hey, enough words, you guys. Let's see how this theory actually plays out. And VSEPR theory predicts that all compounds will be one of 3 basic shapes, each with their own corresponding types of bond angles. So let's write these down. Okay, so VSEPR theory predicts that a compound will be one of 3 basic shapes, each with their own corresponding types of bond angles. Bond angles, okay? Okay, so the first basic shape is, number 1 is tetrahedral. Tetrahedral. And go ahead and put in parentheses right next to it 109 degrees. Okay, because tetrahedral compounds have bond angles of 109. All right, so hey, let's write a couple more things down about this guy. Because tetrahedral compounds, these consist of 4 sigma bonds or lone pairs. Okay, so hey, this consists of 4 sigma bonds or lone pairs. Okay, and remember you guys, a sigma bond, this is just another way of saying single bond. This is in comparison to multiple bonds, which are known as pi bonds, right you guys? Hey, the point is, you'll see that tetrahedral compounds only have single bonds or lone pairs. Okay, they have some combination of 4 single bonds or lone pairs. If you ever see multiple bonds, pi bonds, like those in double or triple bonds, then you know that that compound is not going to be tetrahedral. It'll be one of the other shapes that I show you next. Okay, but hey, let's finish up with tetrahedral compounds first, and then we'll get on to those. So, hey, a tetrahedral compound will have some combination of 4 single bonds, sigma bonds, and lone pairs. Let's see an example. Okay, so let's just take CH4 for example, okay, methane. Okay, so for example, CH4, this is also known as methane, and CH4 looks like this. And I've drawn this compound with some 3D perspective. So if this is your first time seeing these dashed and wedged lines, don't stress, okay, because they just represent single bonds. These are still single bonds right here. But a dashed line just means that this bond is going into the board. A wedged line like this one means that that bond is going out of the board at you. The reason why we draw them like this is just to give the compound some 3D perspective. Because hey, this board is flat, right? And we needed a way to show that this compound was 3D, with atoms not only in the plane of the board, but going into and out of the board as well. But anyways, so what I'm saying is that this hydrogen is going to be coming out at you, this hydrogen is going to be going into the board, and these two hydrogens right here are in the same plane as the board, okay? So, hey, you should notice that this compound is connected by all sigma bonds, okay? So sigma bond, sigma bond, sigma bond, sigma bond, okay? And hey, a sigma bond is just another name for a single bond. You can use those words interchangeably. They mean the same thing, right? So, hey, the thing I want you to notice is that only single bonds are present in this compound. And that is the reason why this compound is the shape that it is. The fact that there are 4 single bonds, 1, 2, 3, 4, 4 single bonds extending from the central atom, this carbon, makes this compound tetrahedral in shape. You'll notice later that double and triple bonds change the shape of a compound. But for now, let's see why having 4 single bonds would give this compound a tetrahedral shape and bond angles of 109 degrees. Okay, so hey, you can fill in the bond angle here if you want. The bond angle between all of these are going to be 109, 109, 109, 109 degrees. Okay? Okay, and this is an important distinction to make, you guys, because hey, normally when we saw CH4 drawn in a Lewis structure before, it just looked like this. We just drew a carbon connected to 4 hydrogens with 4 straight lines like this. And if you just draw like this implies that, hey, this is a 90-degree angle, 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 okay? And all of these atoms are in the same plane. But this is not the case, because if you look at how CH4 actually exists, it exists in 3 dimensions with bond angles of 109 degrees, okay? That's why we're stressing this to you right now. Okay, so let's start off with a compound that only has 2 bonds. And don't write this down here, okay, because it doesn't belong here. We'll get to this in a little bit, okay? This is just an example, okay? So, hey, let's start off with a compound that has 2 single bonds. So, hey, let's pretend here's an atom in the center. He's going to be connected to an atom there on the side, and then another atom here on the side, okay? So, hey, do me a favor and pretend that these markers are bonds. So this is going to be a bond here, this is going to be a bond here, and there's an atom on the side, in the center, and on this side, okay? So, hey, these markers are bonds. So here's 2 electrons connecting an atom here, a first atom here, a second atom here, and a third atom here. They're all connected by these bonds, okay? So, hey, let me ask you a question. If bonds are made out of electrons, and electrons are negatively charged, and negatives repel other negatives, then what position would these markers want to be in, these electrons want to be in? What I mean is, if all 3 of these atoms were connected, would they want to be arranged like this, with their bonds really, really close to each other? Or would they want to be arranged like this, with their bonds as far apart from each other as possible? As far apart from each other as possible, right? And so they'd be in a straight line like this. A straight line like this, okay? Let's see what happens if a compound has 3 sigma bonds. Okay, so if we added a 3rd sigma bond to the central atom right here like this, what would happen is, in order for these bonds to get as far from each other as possible, then they would split up into this triangular shape, and it's called a trigonal planar shape, with these bonds being as far apart from each other as possible. So this bond is as far apart from this bond as possible, is as far apart from this bond as possible, is as far apart from this bond as possible, in a trigonal planar shape that looks like this. Okay, with these bonds shaped in this trigonal planar shape, okay? And this is actually the other two shapes that we're going to be dealing with. This one where you only have two single bonds, this is a linear shape, okay? This one where you have three single bonds, it's called a trigonal planar shape, but we'll get to this when we talk about the other two types of shapes you can have with the other two types of bond angles, okay? So, hey, don't write this down here. We're going to get to it in just a second after we finish up tetrahedral. So let's see what happens when you add a fourth bond to the mixture, okay? Okay, so how would a compound look like if it had 4 sigma bonds? Well, at first glance, you'd probably think that to get as far away from each other as possible, the bonds would be arranged in a cross shape like this, with these bonds pointing in 4 opposite directions. And this is a good guess. But we know that when 4 atoms are single bonded to a central atom, it makes a tetrahedral shape that looks like this, right? So, hey, let's see how that happens. Okay, so if 3 bonds are arranged like this in this trigonal planar shape, all in the same plane, let's see what happens when a 4th bond comes in. Okay, so when a 4th bond comes in, then the trick is to think in 3 dimensions, because these atoms can all try to get as far apart from each other as possible in the same plane like they are now, or they can choose to utilize all the space in front and back of them, okay? And the answer is, of course, they use all the space in front and back of them to get as far away from each other as possible. So let's see how this works, okay? Okay, so this guy right here, he's like, hey, look at all this space in back of me. I'm gonna just move back. Okay, so he moved back. And then this guy, he's like, hey, look at all this space in front of me. I'm gonna just move forward, right? And then this guy wants to get in on the action too, so he moves a little bit to get as far away from the other bonds as possible. And eventually, it ends up in this tetrahedral shape type of thing, okay? Like this, okay, with these two bonds in the same plane, this hydrogen coming out of the board like this wedge, and this hydrogen going into the board like this dash, okay? So, hey, sorry you guys, I know that this is really hard to see, but I'm just trying to help you visualize what's going on, okay? These bonds were just trying to get as far away from each other as possible, okay, to make this tetrahedral shape. Go home tonight and build an actual tetrahedral compound with your chemistry set if you want a more accurate view of how these bonds are arranged, okay? So, hey, that was an example of a tetrahedral compound with all single bonds. But I told you, it could also have lone pairs, right? So, hey, let's see an example of a tetrahedral compound with some lone pairs on it. Okay, so let's take, for example, NH3. Okay, and NH3 looks like this.